We are discussing homonuclear diatomic molecules. We have already talked about things like H2 plus, H2, He2 plus and even He2, which is not really a molecule but shows some energy minimum. Now we are going to talk about a little bigger homonuclear diatomic molecules, things like F2, N2 and so on and so forth. Now the moment we discuss second row homodiatomic molecules, a problem creeps in. The problem is this: if you think of hydrogen atom, in hydrogen atom actually the energies of 2s and 2p are the same. However, for multi-electron atoms the energies of 2s and 2p are not the same. That is because of things like shielding and screening, which you are going to learn in a different part of this course. So 2s and 2p are no longer degenerate. The question is, when the molecules form from these atoms, do we consider them to have different energy or same energy? Because one very important rule of thumb for molecular orbital theory is that atomic orbitals participate in linear combinations only when they have compatible geometry and comparable energies. So if I draw this picture where 2s and 2p are very different in energy, then the MOs that I expect to get are these. The two 1s orbitals participate in a linear combination to give me 1 sigma and 1 sigma star. Now here 1, 2, 3 these are just well sort of roll numbers. 1 sigma means the first sigma orbital that we have obtained going from bottom up in energy ladder. 1 sigma star means the first antibonding sigma orbital that we have obtained, so on and so forth. So 2 sigma would form from the two 2s orbitals, and if you go to 2p orbitals, generally it is conventional to define the internuclear axis as a z axis. There we will consider the 2pz orbitals to combine to give us the sigma combination, that is 3 sigma, and corresponding antibonding orbital is 3 sigma star, and px and py. So x, y, z, this is the bond. Now the two px orbitals can give you pi overlap, right. So they will form one linear combination to give you one pi orbital. The two py orbitals give you another kind of pi overlap, and that gives you the another kind of pi bond. But this along x and this along y, they have the same energies. So what you get is you get degenerate pi orbital, degenerate pi star orbitals, and the degeneracy is 2, doubly degenerate pi orbital, doubly degenerate pi star orbital arising out of linear combination of px and linear combination of py. See, once sigma bond is formed, the axes are defined. Now px and py cannot combine, this px and this py cannot combine, it has to be px pi interaction, py pi interaction, that is what it is. Okay. So question is, what should we do? Should we do it like this? Should we do something else? Well, if we go with the model where there is separation in energies of s and p orbitals and you get molecular orbitals like this as expected, then this is what you expect for dinitrogen. For dinitrogen, how many electrons are there? In the valence shell you have 5 electrons. So if I neglect this, we do not even have to neglect, you can fill in the electrons here, but the point is the highest occupied molecular orbital in case of hydrogen then would be a pi MO. What is the implication of having HOMO as a pi MO? The implication is that this dinitrogen molecule should then be susceptible to addition reactions. So in the organic chemistry that we learned, we know that we do bromine water test for say an alkene. Why? Because you add bromine, one bromine atom goes to this carbon, one bromine atom goes to that carbon, this pi bond breaks, and instead of a CC pi bond, now you have two CBr sigma bonds. Same thing should have happened with nitrogen. Okay, nitrogen is a gas, you bubble it through bromine water should get discolorized then, and you should get something like BrN, NBr. never happens. In fact, nitrogen is very inert, that is its role in the atmosphere. If we did not have nitrogen in the atmosphere, perhaps everything would get oxidized or catch fire or something. So, it dilutes things. It is a very inert gas, and because of its inertness, have you heard the name of Professor Acharya Prafulla Chandra Rai? Well, the English spelling is Ray, but actually it is Rai. So, Acharya Prafulla Chandra Rai had made a compound in which this dinitrogen was made to react. I encourage you to find out what that compound is called. The compound between mercury and dinitrogen, what is it called, what is the structure. Some skepticism had been expressed later on saying that is not really that molecule, but then it has been now conclusively proved that Professor Rai was correct. He was one of the founding fathers of modern day chemistry in India. And the reason why that was such a big deal is that dinitrogen is so inert. Why is it inert? From this diagram we expect it to be very highly reactive, very highly susceptible to addition reaction. It is inert because, see, if you go back to the situation of your hydrogen, then 2s and 2p have the same energies. So, in a situation that is close to hydrogen, where 2s and 2p orbitals are degenerate or very close in energy, then you have to write an MO like psi sp is equal to some C1 multiplied by, I will call this A and I will call this B, okay. 2sa plus 2sb plus C2 multiplied by 2pza plus 2pzb. Whereas, if the situation is like this, where there is a separation between in energy between 2s and 2p orbitals, then you have to write two different linear combinations. So, you can write like this psi 2s is equal to, oh I wrote psi 2s here, so I will write phi then, phi's are atomic orbitals, phi 2s A plus phi 2s B, and I have to write psi 2pz equal to, I can write plus minus here, and I can write some C3 here. I am writing C3 because I have forgotten whether I wrote only one C1 or whether I wrote C1 and C2. So, C4 multiplied by phi 2sa minus, well, psi 2pz plus minus phi 2pz. These two will not mix. You have two situations. So, there are other cases. If you use the energy diagram I showed you, then the magnetic property of fluorine is not explained, magnetic property of F2 is not explained rather. So, there are many such discrepancies. So, the current understanding is that when the atoms are smaller, when they are closer to hydrogen, that is when they are going to have this kind of a situation, where there will be sp mixing, you can think, or rather S and P are close in energy. In fact, I do not even like to draw like this, these are from Atkins, but what they are saying is that some mixing will be there. So, you are going to get this sequence of molecular orbitals. When there is no mixing, in the situation where the atom is large and energies of 2s and 2p are very different from each other, then you get the energy diagram that you expect. So, somewhere there is a switch in sequence. Look at this pi and look at this sigma. When you consider mixing, this sigma orbital is at a higher energy than pi. If you do not consider mixing, then the sigma orbital is at lower energy compared to pi. And looking at experimental trait, what we see is that, what we say is that for dinitrogen, definitely the HOMO has to be sigma, that is why it is non-reactive, and it fits in nicely if you use the model where sp mixing has taken place. However, for oxygen that is not the case. So, we find that there is a switch over in sp mixing traits when you go from nitrogen to oxygen. Why is it between nitrogen to oxygen? Nobody knows. It is just an experimental result. There is no way from basic theory that we can say that this is how it should happen and this is how it should not happen. It is like that is the experimental observation, right. So, this is something that I believe you have studied in 11 and 12 also. That is what we learned about homonuclear diatomics, and now we are going to go over and discuss heteronuclear diatomic molecules.